Remember, it's calorie. We said calorie is simply going to be a unit that we'll use in this class to represent energy. And I told you the way in which they define calorie is the way that they went about defining it, as they simply said, hey, we're going to take water. We're going to have 1 gram of this H2O. We're going to put energy into it. And we're going to simply say maybe the water is at 20 degrees Celsius here. We're going to raise this 1 gram of water by 1 degree Celsius, so 21 degrees Celsius. Once again, 1 gram of H2O. They said the amount of energy required to raise it, in this case by 1 degree Celsius, we're going to call that simply a calorie of energy. That's its definition. And if you think about it, water is used a lot of times as a reference. Celsius scale. We said, hey, you know what? Where it freezes is 0. Where it boils at 100, let's do some even intervals between 0 and 100, and we got our Celsius scale. Water was used once again to come up with this value of energy that we're going to end up calling 1 calorie of energy. Now, what we're going to do is we're going to jump to the next slide. On the next slide, you're going to see this thing known as specific heat capacity. And if you listen to the definition, specific heat capacity is defined as the amount of energy required to raise 1 gram of a substance by 1 degree Celsius. So the amount of energy required to raise 1 gram of substance by 1 degree Celsius, which means that if we think about it, the specific heat capacity for water is going to be what? 1 calorie. Exactly. And one of the things that we're going to see is that when it comes to the specific heat capacity, the symbol that we will use will simply be the symbol C. So one of the things that you'll notice I'm going to do a lot of times, I'm going to say C of H2O. Simply saying, hey, I'm talking about the specific capacity for water here. Is equal to, well, it's 1.00. You can put as many zeros as you want here. It's really an exact number. That's what they defined as being. And then I put calories. And what you'll notice is that the units they have in the table here is grams per degree Celsius. And it shows it right there. Cals, grams per degree Celsius. And you might ask yourself, well, yeah, that's kind of interesting unit to kind of have there. But if you look at it closely, it actually makes sense how they did it. All they really did is the following. They simply said that, hey, if we look at this, the definition of specific capacity, it takes 1.00 calories to raise 1 gram by 1 degree Celsius. But of course, the ones are just going to divide into it, and it just gives us a unit that looks like this here. But once again, that's the amount of calorie required to raise, in this case, 1 gram of water by 1 degree Celsius. So watch this here. I'm going to start, I guess I'll start here. 1 gram of H2O. I'm going to put in, once again, a whopping 1 calorie of energy. Water, in this case, is going to go from a temperature of 20 degrees Celsius all the way to a temperature of 21 degrees Celsius. Somebody help me out. If you look at that table, it tells you that the specific heat capacity for glass, so C of glass, happens to be equal to 0.20? Yeah. All right. Cals per grams per degree Celsius. Watch what's going to happen here. That you're going to start to notice something. If I have 1 gram of glass, and I start off at a temperature of 20 degrees Celsius, when I put in 0.2 calories of energy into this thing, I'm going to get, in this case, the temperature of the glass to go up to 21 degrees Celsius. Because, hey, glass says I don't need 1 cal. All I need is 0.2 calories in this case. Ah, you're 1 step ahead of me. Watch what's going to happen. 0.2 calories. I'll put another one in. 0.2 calories in. The temperature of the glass is now going to be at 22 degrees Celsius. Let me do this a couple more times here. Put another 0.2 calories. Temperature of the glass is 23 degrees Celsius. Put in another 0.2 calories. Temperature of the glass is now going to be at 24 degrees Celsius. One more time. 0.2 calories. Temperature of the glass is 25 degrees Celsius. Question I have for you. going from here all the way down here. What's the total amount of energy I put in there? 1 calorie. If you look at it, water says you give me 1 calorie of energy, I will go from 20 to 21. You give me another calorie of energy, I go to 22, then 23, then 24, and 25. Water's like, hey, water but glass says you give me 1 full calorie of energy, I'm all the way down here at 25. You give me another calorie of energy, I'm at 30. Which means that things that have low specific heat capacities are going to heat up very quickly. The same thing. They will cool down. Hey, if I lose 1 calorie of energy, I'm all the way down here. I lose 1 calorie of energy, I'm right here. So we think about the water, specific heat capacity. Water has a large capacity to hold on to heat before its temperature starts to go up. Hey, happy birthday to me. Happy birthday to me. Happy birthday, Mr. Hurlson. Happy birthday to me. Oh, look at this. I got this candle right here. I gotta be this cool kid on the block, because you know, when it's your birthday, you don't want to just be like, and blow it out. Instead, what do we normally do if we want to be cool?
Use your finger.
We use our finger. You're like, hey, watch this. If I do this, ow! Burn myself. What can I do to prevent myself from burning myself? No, nobody's ever seen them do it. That's it. Say it louder.
Lick your finger.
It's because it absorbs the saliva in your finger absorbs the heat.
The water, not your finger, exactly. So the water in your finger that you put on your finger is gonna say, hey, you know what? I'm gonna take the heat in. But because I have a high specific capacity, I'm not gonna raise the temperature high enough that it can actually burn you. Your skin is different. Your skin will say, hey, if I didn't lick my finger, it's gonna take the heat and just shoot the temperature of my skin up really high to the point where it will burn me. That's why, just make sure that if you are the cool kid on the block, just make sure you lick your finger, because if not, you're not gonna be that cool person. You're gonna be like screaming, once again, from burning your finger.
Or we could not play with fire.
No! Once again, we're not really playing with fire. We are knowledgeable of science, and we're able to take advantage of the specific event. Matter of fact, what you can do is next time when it is your birthday and they sing happy birthday to you, you say, watch this. I'm going to show you the specific capacity of water happens to be extremely high. Lick your fingers, and once again, you're demonstrating science in this case.
Does your wish still come true though? Because doesn't it only come true if you blow out the candle?
I don't know. I'm going to have to look and refer back to the happy birthday, what would we call it, handbook of happy birthdays, and see what it says with regards to whether or not your wish will come true. Does it have to be blown, or does the candles just need to be extinguished in this case? Yes, absolutely. All right, here we go. So let's continue on with the notes here. So one of the things we're going to see once again, specific capacity, the amount of energy required to raise, in this case, 1 gram of water, 1 gram of substance by 1 degree Celsius. Keep in mind that in tonight's homework assignment, I will be giving you this table because you're going to need it in order to do some calculations here. Also, when it comes to the test, I will give you this table as well. The only thing that I will not give to you when it comes to the actual test is on your test, you're going to have this exact same table, but it is going to be minus one thing. And this right here, box is going to be empty. You're only responsible for knowing the specific capacity of liquid water. Well, we already said it's just 1 cal per gram degree Celsius. Everybody else, I'll get the specific capacity of the solid versus the actual vapor in this case. So let's continue on here with the notes. So just pointing that out. And remember, I've always told you you're kind of responsible for water. You know, have no melting and freezing point. We know the density of water. Well, now you know the specific capacity of water as well. All right.
Why did they choose water? Is there something?
I mean, you gotta think about it. The nice thing about water is kind of like this thing that we just encounter a lot of, that we have a lot of it. And it's easy to get it in its pure state as well. I can deal with the frozen, I can deal with the liquid, It's just something that with great abundance, so it's probably just the easiest thing to work with in this case. But they could have chose anything to reference it to if they wanted to. All right, continue on right here. So on this slide, it says it once again, substances that have high specific capacities right here are going to take a long time to heat up and also cool down. Substances that have low specific capacities will heat up really quickly and cool down very quickly. Water has a really large specific heat capacity relative to other substances. You'll notice right here that I gave this specific capacity of liquid water as being 1.00 calories per gram degree Celsius, or you can write down 4.184 joules per gram degree Celsius. And the reason why this kind of works is, if you remember, 1 calorie is equal to 4.184 joules. So all they did was just simply take the 1 calorie that's sitting here, and in lieu of it, put the 4.184 joules. What's the difference between the two? Well, it just depends upon what I'm asking on the homework. Some problems I might say, give me the answer in joules. Choose this one. But still, you don't even have to use that one if you don't want to. You can still use this one. We'll see in a second. It's just going to kick out the answer in calories. And then just use this equivalent statement here to allow you to get to joules. And we'll see how this works in a second. All right, and let's move on. So what you're going to see right here is we're going to take a look at how we're going to go about calculating heat. And calculating heat is easy. If you remember, we said Q is the symbol that we use to represent heat. M is simply going to be the mass. C is going to be our specific capacity. And delta T is going to be the change in temperature. So long as you give me the mass, the specific capacity, and the change in temperature, I can calculate how much heat that substance took in. So a good example of how your homework might look tonight. It might look something like the following right here, where I say, hey, we got 25 grams in this case of liquid water. It's being heated in this case from 34 degrees Celsius to 77 degrees Celsius. What is the amount of energy being added in this case? You'll simply say, well, Q is equal to M times C times delta T. And your homework assignment tonight, I do expect to see you substitute in with the units. And I have to say that for the test, when I was grading it, I was very proud of a lot of the students. A lot of students showed their units. Even for the R, they put liters, atmospheres, Kelvin moles. I was like spot on. There were a few students which kind of left that off, and I just docked a little bit from it. But for the most part, overall, did really well. Specific capacity for water, we said it was going to be 1.00 calories per gram degree Celsius. Once again, final temperature minus the initial. Please remember it's final minus the initial. That's one of the common mistakes that's written down or missed. So it'll be 77 degrees Celsius minus 34 degrees Celsius. So I expect to see this. Drop your units and just give me the final answer in this case. And keep in mind, the answer's right there on your actual notes. And the reason why I kind of gave the answers is this, you're just plugging it into the equation. That's it. It's simple and easy. Only thing I want to point out, in this process up here, if it goes from 34 to 77, does it have to take in energy or does it have to release energy? It takes in, which means that, is it endothermic or exothermic? Endothermic. And if you look at it, I know for a fact it's endothermic. How do I know? Because the answer comes out to be positive. And remember, we said that plus, if we ever see that the number is positive, it always means that it's an endothermic process. It's taking the energy and it's growing with energy. Now, for this problem, watch what's going to happen here. I'm going to take the exact same problem on the next slide. And I'm going to say, instead of going from 34 degrees Celsius to 77, I'm going to go from 77 and cool this down to 34. And if I do that, and substitute it to my expression here, the mass is the same. Specific heat capacity is the same, but if you look at it, the final temperature is now 34. The initial temperature is now 77, which is gonna kick out, in this case, a negative 1100 calories. Remember, there is no such thing as negative energy. You can't have it. Energy is always gonna be some positive value. But the negative simply says that, hey, for this process that we're looking at, the energy is flowing out. So if you see a negative, all that simply means is it's being released in this case. And that's what the water has to do. It's got to release energy if it's going to go from 77 to 34. Now, in your homework assignment, I'm going to give you, of course, something more worthy of honest chemistry. I'm going to give you one that's tricky like this. where I'm going to say, hey, we got this number of calories of energy is added to a sample of water. The water is going from 37 degrees Celsius to 85 degrees Celsius. What is the mass of the water? And you're going to say, hey, you know what? I got this expression here. Oh, he gave me Q because there it goes right there. Mass, in this case, he wants me to find. Specific capacity of water, well, that's 1.0 calories per gram degree Celsius. And my delta T, of course, can be found over here. So in this case, I'm being facetious. Come on. All you're going to do is literally substitute the numbers in and solve for the unknown in this case. And when I solve for the unknown, once again, show units here. All the units I'm showing right here, you don't have to show all that. But just make sure you do give me that final answer. Once again, kind of conveying the correct numbers to negative figures, plus or minus 1. I got 2.16 grams of the water here. And your homework assignment, yes?
Oh, I was just gonna say, can we like take the formula and rearrange it so from S and then plug the numbers in?
I'm going to say, this is one of the things that I was talking to Mr. Grace came in my classroom once, and I was kind of like telling students, like, you know, hey, write this down and then kind of solve it. And Mr. Chris was like, no, what you should do is you should go ahead and take the equation in this case and then solve in this case for the mass. I'm going to say that's fine. I'm just saying be careful. Because sometimes I get it all the time. It actually happened on this test here where a student, instead of writing into the ideal gas law, she solved. It was something like PV equals nRT. And then she said N is going to be equal to RT over PV. I had to take off points in this case. Because in a sense, what you're telling me the equation is PVN is equal to RT in this case. So long as you can solve it algebraically, you solve the equation correctly, by all means do it. But if you show me this, and then somehow you mess up with solving it, I can say at least you're plugging into the calculation correctly. But I just see students like flip-flop this and they end up losing points because they didn't actually kind of, so it's your choice. All right, but just be careful. This last slide right here, and we're going to look at something a little bit more worthy of honors chemistry. Only thing I'm showing you here is in your homework assignment, you're going to be having things other than water. And in your homework assignment, which is going to be unlike your notes, I'm not going to have this written down. I'm just going to say, hey, a sample of iron, which is 42 grams, is cooled from 50 degrees Celsius to 27.0 degrees Celsius. And what you're going to do is you're just going to go to your chart. And I'm going to show you on your homework assignment tonight, it's going to have that exact same chart as for the heat capacities. You're going to have to go to the chart and then just pull this value from the chart, realizing I need it in order to solve it. But still, if I look at the problem, it's the same sort of problem to substitute in my mass, substitute the specific capacity now for iron. Hey, final temperature is 27, initial temperature is 50. I can see this thing's going to kick out a negative number because energy is being lost in this case. You'll notice that it kicks out the answer in this case in calories. But because they asked for joules, don't forget that 4.184 joules is equal to 1 calorie. And once again, by the time you get to the test, you'll know that number, just like you know 760 millimeters of mercury is equal to 1 ATM. All right, what we need to do now is look at something a little bit more worthy of honors chemistry. This is a problem worthy of honors chemistry. So let's look at it. And what I'm going to do is I'm going to read the problem. And then after reading the problem, we're going to see if that light bulb goes off and see if you can solve this problem here. So it tells me a piece of silver metal at a temperature of 96 degrees Celsius is added to 25 grams of water at 35 degrees Celsius. The final temperature of the mixture is 62 degrees Celsius. What is the mass of the silver metal? And the heat capacity of silver happens to be 0.0558 calories per gram degree Celsius. All right, based upon that, anybody see the solution yet? No? All right, let me read it one more time. Sometimes you gotta read it twice. A piece of silver metal at a piece of silver metal at 96 degrees Celsius add 25 grams of water at 35 degrees Celsius. Final temperature of the mixture is 62 degrees Celsius. What is the mass of the silver? How about now? Not what? What are you gonna say? What was your thought? I can't average. The only reason you can't average, because if I had water, so I had water, and they both have the same specific capacities, but the problem is that this is silver, And the water has like a different specific heat capacity, so it's not gonna match up. We're gonna kind of average things together. But watch this. Sometimes a picture is worth, oh, how many words is it? Is it still 1,000? I know, inflation could have went up a little bit here. All right, so it's worth 1,000 words in this case. So what we're gonna do is let's see if we can draw a picture to kind of illustrate exactly what's going on here. Where's my black Expo marker? Here we go. I got this piece of silver this person is holding up right here. That piece of silver, we're gonna say this right here. Temperature of the silver initially happens to be at a temperature equal to 96 degrees Celsius. Gotcha. Over here, the beaker. I got my water. So I'm gonna say right here, I got water and I got 25 grams of H2O in here. I'm gonna do this right here. Temperature of H2O initial happens to be what we got right there, 35 degrees Celsius. Now, what we're gonna do is we're gonna take the silver and we're gonna plop it right into that water. So here we go. Here goes my beaker, and here goes my water and my silver kind of added together. And we simply said the temperature of the mixture is gonna be a final temperature of 62 degrees Celsius. All right, here we go. Let's see if we can solve this thing. I'm gonna kind of lead you in a way in which you're gonna hopefully see what the solution to this problem is gonna be. Question for you. Who's losing heat in this case? Silver or the water? Silver, okay. What symbol do you use to represent heat? Q. And if silver is losing the heat, what do I need to put in front of the Q? Positive or negative? Negative, okay. Who's gaining the heat in this case? Water. So therefore that's gonna be positive in this case. How can I go about solving this problem?
Wait, so could you like put that on the side? Like, could you like push it together into one equation?
But what did we say? We said something.
Can't you set them equal to each other?
We can set them equal to each other.
Because the same amount of heat that the silver is losing is the amount of heat that the water is.
And that's what this equation said. It said heat lost by silver equals heat gained by the water. And if you think about it, we know what Q is. We can go right here and say, hey, negative, we'll substitute for what Q is. It's the mass of the silver times the heat capacity of the silver times the change in temperature of the silver is equal to positive mass of H2O. Let's turn this off here. Times the heat capacity of H2O times the delta T of the H2O. So long as we acknowledge that we got two different substances coming together, and I told you this in the last time we were in class, I said, hey, if we take two things and we bring two things together, we're always going to need to define who is the Q negative and who's the Q positive. And then we'll just set up our expression and substitute in. Because if I look at it, what do I know? I know that I'm trying to find the mass of the silver, so I'll leave that as a variable. The specific heat capacity of the silver, well, it gave it to us in the problem here. It says, hey, it's 0.0558 cows per grams degrees Celsius. Change in temperature, well, the final temperature of the silver is going to be what? 62, because that's its final resting place, 62 degrees Celsius. The initial temperature of the silver, well, they gave that to us. They said the initial temperature is minus. And we got 96 degrees Celsius, final minus the initial. So I got you. Is equal to, so I'll put my equal to right here. And now we're going to the mass of the water. And they told me in this problem that the mass of the water happened to be 25 degrees Celsius. Or not 25 degrees Celsius, but 25 grams. Times for the heat capacity of the water, well, we already said it's going to be 1 cal per gram. Matter of fact, I'll go 1.00 cal per grams degrees Celsius. The next thing is we got our final temperature, which we said is still 62 degrees Celsius. They're both the same final temperature. Minus the initial temperature. Well, the initial temperature of the water was 35 degrees Celsius. And here we go. All we're going to do is just solve, in this case, the right-hand side of this expression. And then we'll solve the left-hand side and ultimately solve for the mass of the silver. So over here, let's see what we got here. 25, well, we'll do this. 62 minus 35 times 25. So I'm gonna go in here. Should I do this? I'm gonna do it anyways. Should round at the end, but I'm just gonna go ahead and round really quickly here. So it's gonna give us 680. Over here, I'm gonna multiply this stuff together. So I'm gonna take 62 minus the 96. That gives me negative 34. But I got a negative out here that's gonna cancel that negative and force this thing to be positive. And then multiply that times 0.0558. And what I'm gonna end up getting now is 1.9 times the mass of Ag. And then when I solve this, I'm gonna say the mass of the silver is equal to, well, 680 divided by the 1.9, and that's gonna end up giving me 680 divided by 1.9. Looks like we get 360. Got it. What's wrong? What? Thank you. Units, grams. Do not be that person who does all this work. I guarantee you, somebody in this class, well, not to say in this class, out of one of my sections, when we have a test and I give a problem like this, did I just say that? I did. When I give a problem like this, there's gonna be somebody who's gonna do all this beautiful work, and they're gonna be like, hey, Mr. Harrelson, take one free easy point by leaving the units off. I had a couple students on my AP test. Oh man, they had some hard problems. Left the unit off, and unfortunately, I had to take 1 point. And the problem was only worth 2 points in this case. 1 point for this right here, and 1 point for the answer with the unit attached to it. Yes. Yes.
Do you include the sig figs from the capacity table?
Do you include you?
Like,
No, because that's actually, we're treating that as a constant. So we're gonna treat that as unlimited numbers.
So like
Figures.
from the, okay.
So yeah, so that one you don't have to worry about. All right, here we go. So let me point out what we're gonna do here. So what we're gonna do for homework. So let's go to Veracross. So go to Veracross. You're gonna go to chapter number 10. You're gonna pull up the worksheet packet. All right, you go here as well. And you should see once again our chapter 10, the worksheet packet. Come on. The review worksheet's already up there with the answer key. All right, here we go. Wrong thing. Go back. I want the worksheet packet. Down here. So if you click on the worksheet packet, what you're gonna notice is your homework is gonna consist of this first worksheet right here. Now let me erase what's up here so you can see it. You'll notice that on the worksheet, I do tell you, hey, for these problems that you'll be solving, make sure you show the substitution in, showing your units and giving that final answer with the correct sig figs in the units here. Once again, these are kind of the equations that you'll be using here. Here goes your table of specific heat capacity that you might have to pull from. Keep in mind, for some of the questions are not going to be anything which you have to calculate. Like, hey, what's the difference between heat and temperature? Well, you just give the definition. Number 2, same thing. No calculation required. Number 3, you'll go through and you'll do the calculation. Now, one of the things you're going to have to get used to is, hey, do I just use a Q mcΔT or is it a Q negative equals Q positive? Well, it's pretty easy to figure out which one you're going to use. If I use Q negative and Q positive, guess what I got to have? 2 things, exactly. If it's not 2, then it's going to be, hey, Q equals mcΔT, right here. How much energy is absorbed when 60 grams of iron is increased from a temperature of 27 degrees Celsius to 425 degrees Celsius? That's not 2 things. One other thing to point out really quickly, for number 4 right here, you're not calculating anything for number 4. I want you to kind of think your way through it. And you'll read over it and just see if you can kind of think your way. For number 5, you'll go through, once again, calculate it. I don't see 2 things here. Number 6, I got bismuth is placed in water. Uh-oh, that's 2 things. Maybe I might need to use my Q positive equals Q negative. So you're gonna go through and do problems 1 through 10. Now, with that said, how much time do we have left here? We got 7 minutes.